Well, it's a great pleasure for me to be back in Singapore. This is my second visit here. The first one was with Lars back in 1980, and the place has certainly changed in that time. It's also a pleasure to talk about, this is an old topic for me, actually the first research topic I worked on, and it also relates to discussions that I had with Professor Salam just as I arrived at Imperial College. So that's what I'm going to tell about work with Alan Perkins, Hong Liu, and Chris Pope. But let me just go back to 1978. Just as I arrived at Imperial, I had a series of conversations with Professor Salam about the role of higher derivative terms in quantum gravity. Essentially every approach to quantum gravity. In fact, we just had one from Ali Shamsuddin, which produces curvature squared terms in the effective action. And so that's what I wanted to talk about. Of course, we knew about this from the work of 't Hooft and Veltman. I'm going to discuss including terms quadratic in the curvature, Weil squared and R squared, or of course you can rewrite that thanks to the Gauss-Bonnet identity as R mu nu squared minus 1/3 R squared in terms of instead of the Weil squared term. Now, this leads to a renormalizable theory in four-dimensional gravity, but there's a heavy price to pay for that, which is unitarity. And I'm going to begin by discussing a little bit ways that that one perhaps might try to avoid the issues with unitarity. That's not really the main topic of my talk. I want to talk about what happens when you take these terms seriously and you look at the classical solutions. At the time, back in 1978, Salam and Strathee wrote this paper, arguing on the basis of Froissart boundedness, that is the limitations on amplitudes from unitarity considerations, that one should include these R squared and R mu nu squared terms in the original action and quantization. And they suggested criteria that perhaps could make the ghost not hit you in the spectrum. I have to say, this is one of these Salam papers that I found it hard to read in detail and really understand to the last point. At the end, however, there is this suggestion that there could be a non-trivial, a non-Gaussian fixed point that would play a crucial role in avoiding the ghost. They suggested, in fact, that the ghost might be avoided if there were a non-trivial ultraviolet fixed point for the quadratic curvature coefficients. Now, I don't want to go through the whole history of this. There was a paper by Hove and Tonin calculating the one-loop counterterms. That paper was corrected by Fradkin and Saitlin, and the paper of Fradkin and Saitlin was corrected by Avramidi and Barvinsky. I think it finally reached a fixed point in the calculation of renormalization group coefficients. The end result is that these theories are asymptotically free in the higher derivative couplings. And that turns the picture somewhat on its head. And it's been exploited more recently in an asymptotic safety context, following work by Weinberg, Reuter, and in particular Niedermeyer, who uses this renormalizable R plus curvature squared theory as a stable starting point for the renormalization program, so you know what your family of relevant operators is. And Niedermeyer claims, therefore, using the asymptotic freedom of the higher derivative terms, that there's a non-trivial non-Gaussian fixed point for the Newton constant and the cosmological constant, which then is reached in the ultraviolet, along which there are renormalization group trajectories on which the Hessian has no negative eigenvalues, and so therefore you can avoid ghosts. Now, there are a lot of words there, and if you talk to people in the asymptotic safety community, you get into a big argument back and forth about scheme dependence and so forth, and I don't want to go there. I'm merely mentioning that these are the sort of ideas. You see that this is an idea that was kicked up by Salam, and somehow it's out there. So this is a bit part of the magical aspect of Salam's personality. I don't know if one agrees with the original formulation of it, but this idea that there could be a non-trivial fixed point that is relevant to the issue of ghosts was clearly there. And this, I think, is one of the very first papers in which that idea came up. Now, there are other contexts in which one considers these higher curvature terms seriously. And that's really all I want to do at the beginning of this talk, is to give some motivation for taking the action seriously, and then I'm going to look at classical solutions. And that, of course, that's other context is cosmology, as we just heard from Sergio. I had shown in this paper that the theory of R plus R squared can be equivalently rewritten at the linearized level as gravity plus a scalar field, massive scalar field, which is not a ghost. This was later generalized by Brian Witt to the nonlinear level, and that was the structure that was used by Starobinsky in his model for inflation. Now, all I really want to say is the number I didn't write in front of this is large. It's not a quantum-sized number, but rather it's probably something on the order of 10 to the 9th, as we just heard earlier today. That puts the relevant mass scale about 5 orders of magnitude below the Planck scale. All I want to say is there can be an order of scales in which these types of terms can be relevant to the effective action, and if that's the case, when you come to study effective solutions of the effective theory, you should take these terms into consideration. So that's really where I begin, is a classical approach. Start with this sort of action and see what the solutions look like. So here we have the action with an R Weyl squared term and an R squared term. You vary and produce these 4th order field equations. I've also provided for some discussion a stress tensor on the right-hand side, and I'll take that to be an ordinary stress tensor that you get, for example, varying the standard model action. Okay, so that's the task, is to go away and find the solutions of those field equations. Now, we're going to look for spherically symmetric static solutions to begin with. Actually, that's all this talk is ever going to consider. You get some small gifts. Because of the Bianchi identities, one of the equations is reduced to 3rd order instead of 4th order. You could then use that by differentiating that equation and mixing it with the other one to clean the other equation of its 4th derivatives too. And your gift is you therefore end up with 2 equations of 3rd order. That's as far as the gift goes. That's one of them, and that's the other. So that's the task for the student, to go away and solve the analog of the Schwarzschild solution. Actually, Schwarzschild itself is easily seen to be a solution of this if you set the stress tensor to 0, because every term here involves r mu nu on the left-hand side. Set t mu nu to 0, and you can see if r mu nu equals 0, these equations are always satisfied. So the question is, what else are the solutions? Well, let's go and look at the structure of the theory at the linearized level. If you do the sort of thing that relativists hate to do, is split the metric into a flat part and a fluctuation h mu nu, and you write out the action in quadratic terms in h mu nu, you find this nice structure with spin 2 and spin 0 projectors, which are given here. The metrics here, because we're evaluating around flat space, the indices are raised and lowered with respect to the background flat metric. And when you study the equations, what you find is the following spectrum. You have positive energy massless spin 2, that's the ordinary graviton. Massive spin 2 with a mass given by this, 2 alpha to the minus 1/2, and gamma for the coefficient of r, but with negative energy. That's the ghost. And then the positive energy massive spin 0 with a mass given by. So the alpha and beta coefficients, alpha, remember, was the Weyl squared coefficient, beta was the R squared coefficient. That organization of the action gives directly these modes. So that's the dynamical content of the theory. What I want to look at here, however, is mainly the static solutions in order to see what happens to solutions like Schwarzschild. Well, if we go out to infinity, where the linearized theory is appropriate, then you find that you can solve the linearized equations now in terms of 6, that's 3 plus 3, remember the 2 third order differential equations. You get 6 integration constants here for the a and the b function. B, remember, was the time-time component, a was the RR component of the metric. You have a mixture of 1 over r terms, expected Newtonian type terms, and then you have Yukawa terms here coming from the m2, coming from the spin 2 exchange, m0 coming from the spin 0 exchange, both rising Yukawa terms and falling Yukawa terms. as you would expect from a theory involving massive fields. Now, that's just a generic solution with no specified stress tensor on the right-hand side. When you specify a source, and this is cleanly done at the linearized level, and there are going to be long discussions about doing this in the full nonlinear theory, but in the linearized level, there's no particular trouble. You couple h mu nu t mu nu, and then you get values for those integration constants, assuming asymptotic flatness, so we're going to kill off the rising Yukawas. If you specify a point stress tensor here, so it's the delta 3 of x, only in the time-time component, then you get specific values for those coefficients. Again, I've killed the rising Yukawas. You get 1 over r terms. Of course, the m now becomes exactly as in Einstein's theory, and then you get specific coefficients for the Yukawa terms. Now, another thing that one should note about this theory, however, as opposed to Einstein's theory, there is no Birkhoff theorem here. So there's no statement that outside a certain spherically symmetric source, everything is going to be of the same form. And in fact, you can see that by specifying in this linearized theory a different type of stress tensor. Let's take a kid's balloon, a ball of gas, which has a certain overall mass m. It has a pressure, and it's constrained by an elastic membrane of radius L. Then you find the following expression for the B function. Again, I've killed off the rising Yukawas, but you now get coefficients here that depend upon the parameters of the stress tensor. Unlike in Einstein's theory, if you go back, if you let the radius of the source go back to 0, you return to the point source that we had before. So that's a warning that the structure of sources is going to determine the asymptotic form of the metric in a way much more detailed than we're used to in Einstein's theory. Okay, that was a story about the linearized theory, which is, for asymptotically flat solutions, is relevant near infinity. Now let's look at what happens at the origin in this Schwarzschild coordinate system. So this is deep inside the nonlinear sector of the theory. We'll make a Frobenius type of expansion, asymptotic analysis, asymptotic around the origin, with an unknown starting coefficient in power in R, and then a power series after that for the A and the B coefficient parts of the metric. So we're just solving h mu nu equals 0 here. We're not putting any stress tensor. You find that for S and T, there are only 3 consistent systems. S and T, S can be 1, T minus 1, or 0, 0, or 2, 2, and with these numbers of free parameters. And I have to say that I tried doing some of this back in 1978, and it's a hard job because you have to go out quite far before you catch all the parameters. So this is where power of Mathematica and the power of a good graduate student, Alan Perkins, by the way, needs a job, so I highly recommend him. So we've now calculated the number of free parameters here. Again, this 2, 2, r squared, is the one that has the generic number of free parameters, the 6 that we saw earlier. But there are these other, this is a non-singular family, and this family, 1 minus 1, you will recognize, remember, Schwarzschild is a solution of this theory, and it's going to live in this family. So that's what we studied at the origin. We have the structure at infinity, and now the question is, how do you match them up? What happens in between? So before I go to try to address that issue, let me note that this counting of parameters, 2, 2, 0, 0, 1 minus 1, works well for a type of distributional source that one can consider in the nonlinear theory of relativity, which is a codimension 1 source. Codimension 2 and higher sources produce terrible problems in relativity, as has been studied, but codimension 1 sources can be made sense of. Basically, they're one-dimensional jump conditions you have to make. So we put an eggshell delta function at some small distance epsilon out from the origin, and what you find is this 2, 2 family outside coupled to 0, 0 inside works well with those counts of parameters. You can see that because, remember, there were 3 parameters for the 0, 0 family. That is completely non-singular. It doesn't need any source at all. It's the analog of flat space for relativity. 6 outside, 3 plus 6 is 9, but then you have to subject them to 6 continuity and jump conditions as you cross the shell. That leaves 3 unfixed parameters, and that's exactly what you want, because you want to cancel 2 rising Yukawas at infinity, and then there's one trivial coefficient for the time component of the metric, which can be rescaled. T into alpha t rescaled to G00. So if you, that is exactly, that trivial rescaling you have also, of course, in Einstein theory. So the 2,2 family outside of a 0, 0 sort of vacuum family inside works well. Exterior 1, -1, and 0, 0 solutions, however, would be overdetermined. So we can see that what couples well to a standard distributional delta stress tensor is the 2,2 family. I'll come back to that at the end. Okay, now, how are we going to address the issue of the middle? Well, there is a no-hair theorem, part of a paper by William Nelson, that helps here. Let's consider the coefficient of the r² term to be positive, i.e. non-tachyonic scalar mass. Take the trace of the field equation, and then you get just this nice Klein-Gordon equation for r. If you multiply, so if you let lambda be the norm squared of the time-like killing vector orthogonal to a spatial slice, you multiply by lambda to the 1/2 r, integrate, of course, with the spatial determinant of the metric, square root of h, over a 3-dimensional spatial slice at fixed time. Then, if you integrate by parts but don't throw anything away, keep the total derivative term from over d3x, you get this expression. Now, the point is that these last 2 terms have the same, they're squares and they have the same sign. So this is a classic Lichnerowitz-Israel type of construction. And we'll tell you that r equals 0, providing this total derivative term can be ignored. Now, if you're going out to asymptotically flat spacetimes, r will vanish and the derivative r will vanish. So at infinity, this will be okay. And if you're starting from a horizon, then the lambda will vanish by assumption, because that's what you're talking. That's the norm of the time-like killing vector. So if you start at a horizon, you go out to asymptotically flat infinity, you can then conclude that the Ricci scalar has to be 0. That's a great simplification on the study, and it's basically what allowed us to make some progress on this. Now, this simplifies the theory into essentially the equivalent theory without the r² term, because we've just learned that whether there was an r² term or not in the action, in this class of solutions, which starting from a horizon going out to infinity, the Ricci scalar has to vanish. So we're effectively looking at the theory with r plus Weil squared. And we're starting from a horizon with the condition r equals 0. So if you now do the parameter count, not around the origin, but around the horizon, you find three parameters. And that's interesting because we know that the Schwarzschild solution is in this 1 minus 1 family. It has a horizon, and it has 2 parameters. So within this family of solutions with horizons subject to the r equals 0 condition, 2 parameters are the parameters that are familiar to us from Schwarzschild, and there's one more. So there's just one more knob to turn, a non-Schwarzschild-ality parameter within this 1, minus 1 solution family. And so we can ask what happens if we start at Schwarzschild and turn that knob. What's going to happen? Now, it's pretty clear that when you turn that knob, something has to happen. You've got a horizon. You've got r equals 0, because that's what we're talking about. There was a delicate adjustment of parameters to kill those rising Yukawas at infinity. It's going to go prong. It's going to turn on the rising Yukawa at infinity. So that tells you that the Schwarzschild solution within this family will be isolated, that there will be a specific value of the non-Schwarzschild parameter that will give you Schwarzschild, and as soon as you go away from that, you're going to turn back on the rising Yukawa at infinity. This is also confirmed by a more detailed study using linearization and perturbation away from Schwarzschild, and then proving again no Hare theorems. I'm not going to go into the details of that here for the sake of time, but let me notice that those theorems show you also that there's a certain limitation in the parameters, which is interesting. You can't prove it for all ranges of masses But you can prove it, that, again, that Schwarzschild is isolated for linear perturbations away from Schwarzschild as long as the radius of the horizon satisfies a certain constraint. I'll come back to that in a moment. So the question arises, what happens if you now turn that knob not just a little bit away from Schwarzschild, but a long way away? Do you ever find another black hole solution some distance away from Schwarzschild? Does the loss of asymptotic flatness persist, or does something else happen with solutions arising that cannot be treated by this linearized analysis of deviation? And this becomes a numerical problem. So in consequence of this trace theorem, however, we know that we have to have r equals 0. So the calculations can be effectively done, as I've said, in the r minus phi squared theory. And as you can see from r equals 0, that's a second order differential equation. And now you get another little gift, because actually in this case, the field equation is reduced to 2 second order differential equations. So you're expecting in general 4 parameters. And it's better to study than third order differential equations. So again, we have the Schwarzschild form of the metric. We're going to rewrite the radial part here instead of a as 1 over f. And we're going to assume that we're expanding around a horizon. So b, the time-time component, will vanish linearly in r minus r0 for some radius r0. Then if you analyze the field equations, you find also that f, that's downstairs in the denominator, has to similarly vanish linearly as you approach r0, and accordingly one has a horizon. So we can make the following expansion of b and f, and there are 3 free parameters here. C is the trivial one, r0 is the radius, and f1 is the leading coefficient of f. After you've chosen those, you find that h2, f2, etc., everything else is determined by the field equation. So that, again, is the 3 parameters I talked about. If you write f1 for Schwarzschild is, of course, just 1 over r0. And so we can reparameterize things, this constant parameter, in terms of, write f1 plus 1 plus a delta. Delta is the deviation. This is the non-Schwarzschildality parameter. And now you can do numerical calculations to see what happens as you vary delta. Try to find values of delta not equal to 0 for which the rising exponential behavior that comes on as soon as you turn away from Schwarzschild eventually comes back, and you find a non-zero value of this delta parameter. And in fact, you find that for certain ranges of horizon radii, you can. So here is a phase picture. The dotted dashed line here, of course, is proportional, m proportional to r0. That's the Schwarzschild parameter. But then there is this new branch that occurs, which we just found numerically. So there do exist non-Schwarzschild black holes. And I want to now go on and talk a bit about stability. And I'm going to focus, in fact, in particular on that branch point where some interesting things happen. Now, a proper analysis of time-dependent solutions here is going to be a full numerical undertaking, which we haven't yet attempted. But one can make some general observations. First of all, about the r plus r squared theory. Their study of normal modes done by Brian Witt and Starobinsky shows, in fact, that the Schwarzschild solution itself is stable. The easier thing to study here is stability of Schwarzschild. Stability of the new black hole solutions is harder. That's going to be a purely numerical task. But of Schwarzschild itself, you can look at quasi-normal modes as you expand around the Schwarzschild solution in this theory. And one finds that for the r plus r squared theory, essentially because this is equivalent to just gravity plus a massive scalar.
Just a simple question. Are all these calculations with 0 source?
Yes. Yes. The source was, I'm going to come back to the source at the very end for a certain type of solution. But yeah, we're not asking what's happening deep inside around singularities and so forth. We're just doing this for 0 source. So we find that the Schwarzschild solution in the r plus r squared theory is stable. That, of course, is equivalent to gravity with a positive energy scalar field. Now, when the Weil squared term is present, there's a different structure. There is a phase structure depending on the value of the following combination of parameters. Mu, which we call, so m2 is the mass of the spin 2 mode of the theory. M is the mass of the black hole itself, and m Planck is the Planck mass. Okay, so this is dimensionless quantity. And we find that, again, that branch point where the non-Schwarzschild black holes start occurs at mu equals 0.43. Now, people who have a certain memory about general relativity and the study of black holes might remember 0.43. That actually is a sort of a historical number, because there's a paper by Gross, Perry, and Yaffe back in 1982 about the instability of Schwarzschild in a heat bath. That is to say, if you compactify time, then they found the Linearized operator, which is, the Linearized operator is what you get when you vary the Ricci tensor. So the second order variations of the metric, the Ricci tensor varies by the Linearized operator acting on delta H mu nu. And they find a single negative eigenvalue eigenmode of the Linearized operator in this heat bath. It's the same eigenvalue, and it's essentially the same Linearized mode as found by Gross, Perry, and Yaffe. In this case, we're talking about time-independent solutions. So this is a static perturbation we're talking about. Linearized, spherically symmetric, static solution as you perturb away from Schwarzschild. So that's possible at this branch point. That's the beginning of that second branch, where you can go off on a static solution, but it also is relevant to the issue of time-dependent stability. This is the dividing point between two regimes for stability of the Schwarzschild black holes. For mu less than 0.43, this massive spin 2 mode gives rise to an S wave, that's L equals 0, instability, which is essentially the same as we've said, as the instability of Schwarzschild solution in a class of theories that we've only recently learned make some sense, which is the massive nonlinear theories. Okay, which, it was thought that the nonlinear gravity always suffered from the Boulware Desert ghost, but as we now know from the work of de Rham, Gabadadze, and Tolle, there are nonlinear formulations of gravity without the 6th degree of freedom ghost. And however, in those theories, there is an instability of the Schwarzschild solution, and it starts at exactly the same value, and it is the same single negative eigenmode of the Linearized operator. This history of this involves a correction of an original paper by Brian Witt, who studied this, saw that there could be this beginning of instability of Schwarzschild in the higher derivative theory, but then concluded it didn't happen. But that was prior to the work of Ruth Gregory and Raymond Laflamme in 5 dimensions on the instability of the 5-dimensional string. Why am I talking about 5 dimensions here? The reason is that the subspace, the 4-dimensional subspace of the Gregory-Laflamme problem involves exactly the same equations as for the instability of massive gravity in 4 dimensions. So, and that was pointed out by Babichev and Fabry back in 2013. So we have the following picture of classical stability. I've reproduced that same phase diagram here. Schwarzschild for below the branch point is unstable. Above the branch point is classically stable. And I'd like to be able to tell you something about the stability of the new black holes, but it's too early for that. A final point about stability at the quantum level, Brian Witt's paper also went on to consider the variation of the Euclideanized action, the second variation, and he made the claim also that at the quantum level, the Schwarzschild solution becomes unstable so that this whole line would become unstable. That I merely throw out as an observation on Brian's papers because this is a complicated subject and I don't particularly want to vote yay or nay on whether I agree with it, but I mentioned that as a point about the literature. Okay, so that's for black hole solutions. Now we come back to the other types of solutions that we found. In the view of time, I'm just going to focus on this other one here, which are solutions without horizons. Now, remember the trace no-hair theorem, which said that if you have a horizon and it's asymptotically flat, then the Ricci scalar is 0. That, of course, is incompatible with what I told you about asymptotic structure in general of the theory with Weil squared, R squared, and R. If there's any spin 0 Yukawa term as you approach infinity, the Ricci scalar is definitely not 0. And so, anytime you have a falling Yukawa coefficient for the spin 0, that solution cannot have a horizon. You're just clearly talking about something that is not the black hole that I just discussed. It can't have a horizon. To study what they are, again, becomes a numerical problem. Basically, they're going to live in the 2,2 family. And this was found by Bob Holdham in a theory, well, to simplify the calculation, he set the masses of the spin 2 mode and the spin 0 mode to be equal. We did a similar calculation in the r plus phi squared theory without the scalar mode, and we find exactly the same structure. And here it is sketched in terms of the logarithm of A and the logarithm of B as compared to Schwarzschild. You can see Schwarzschild zings off down here where it has a horizon. But and these solutions of the higher derivative theory asymptotically approach the Schwarzschild solution, but they do have these Yukawa corrections and consequently cannot have a horizon. Instead, they fail to have a horizon and continue in exactly having r squared behavior as you approach the origin in both A and B coefficients. So that 2-2 solution is consistent with the need to avoid the parameter count restrictions on solutions with horizons. Remember, there are only 3 parameters for solutions with horizons. It allows you to have enough parameters in the solutions to cancel in this family the rising Yukawas at infinity. And basically for that, you need the 6-parameter family. That's what the 2,2 family has. This, incidentally, is also the family that can couple to a shell delta function. So what can we say about these solutions? I would note that although it's going like r squared in both the time and radius components of the metric, so the metric is going to 0 at the origin. The curvature, however, is singular. If you calculate, for example, r mu nu, the curvature squared, you'll find an r to the minus 8th singularity. But I note that this is a time-like singularity because we've not crossed a horizon. There's no flip of the light cones. So this is basically what you get from coupling to some sort of delta function source of small radius. You could say that it's somewhat similar to the Coulomb's singularity in ordinary electrodynamics. That's basically what I wanted to say about this family of solutions, and I'm going to end my talk here. There's a point about Salam, however, I want to come back to, which nobody in this conference has mentioned, although Eliezer grabbed this picture before. People seem to have forgotten the twinkle in his eyes. So I don't know what he would have made about all this higher derivative stuff, but it's clear that he had this laughing character, and I certainly remember that. And it's a great honor for me to be able to come to this conference and reminisce on some of the things that I talked about with Salam, some evolution of that. The questions are still open about whether it makes sense to consider these theories, including the higher derivative terms. But thanks for your attention.
Any questions?
Just at a very simple. So the R, if I take the R term plus the R squared term, like Starobinsky, that sort of theory is perfectly okay to all orders, and
yes.
there are no issues of ghosts or anything like that.
No, there are no. One way of looking at that is if you go to this linearized analysis that I did in my PhD thesis. You take the generic theory, you analyze its propagators basically, and split them up into partial fractions. You find massless gravity, which is positive, and then you find a massive gravity, generic massive gravity, okay, with a generic coefficient between the h mu nu, and trace h squared terms, which, however, has a minus sign in front of its action, so that whole thing is a ghost. However, sub-comment, if you now look at the massive gravity with the generic coefficient between h mu nu, and h squared, that, of course, is not the Pauli-Fierz-Matz term. It has its own ghost, right, which is a scalar ghost of the massive gravity. So the spin 0 mode is actually a ghost of a ghost, i.e. it has positive energy. And that is what you can see at the linearized level, and then it continues on to the nonlinear level quite straightforwardly.
And the mass could be whatever you want it to be. in principle.
Yeah, I mean, of course, you should choose the sign of the coefficient beta in order to make it non-tachyonic. But yeah, it can be whatever you want. And as I pointed out, and Sergio was talking, the value that Starobinsky chooses for that coefficient is on the order of 10 to the 9th. It's not small at all. So that would give you at least a long range in which it should be appropriate to consider this type of effective action. Sergio, yeah. Oh, sorry.
I've always had a little problem with the center of the star.
Yes?
Eddington, for example, 1926 previous book, demands regularity at the origin. And you are using basically the same idea. You discuss physicality of the solution at the origin.
Yes.
But among the solutions that you consider, you also consider Schwarzschild.
Yes.
And you cannot say that Schwarzschild is physical near the origin, can you?
Of course, the evolution of a real star is going to have some history of the infalling stress tensor and so forth. So, but
even mathematically, are you going to say that physical considerations don't matter?
They certainly matter. What I'm mainly going to say is that we had enough trouble trying to understand these equations as is. If you want us to do a full-time dependent solution, invite me to UCLA and then I'll be happy to talk to you about it.
How do you justify your interest in the behavior at r equal to 0? In view of the fact that among the metrics that you consider, you include Schwarzschild. This I find a little contradictory.
Well, I don't really have that's kind of an ideological point of view on what you want to make of the actual historical Schwarzschild solution. A real star, collapsing star, of course, is going to have, you're going to cover up parts of the Kruskal diagram and so forth which will be the history of the infall. You have to remember, however, that these theories don't have a Birkhoff theorem, so the asymptotic structure is going to depend much more on the history of the infalling stress tensor. It makes it harder to discuss, however.
I wanted just to say that the interesting fact about this r plus a square, if you do the linearized approximation, you look at the mass term. But when you get the nonlinear potential, the interesting fact is that the Sitter plateau, that is what makes the model interesting for inflation.
Yes.
That the potential has, for large values of the scalar field, has the Sitter plateau.
Yes, that's right.
And this is beyond the linearized approximation.
Right. Yeah.
Yeah, if I understood you right, there's a possibility of getting naked singularities in the asymptotically flat
that's right.
cases. Could those arise from a gravitational collapse of a star or something like that?
Exactly. I mean, what is the final end state? For example, in view of the instability of Schwarzschild at the low mass range. I mean, could this be what happens as a result of Hawking radiation down to a point where finally something collapses? Does it collapse into this sort of situation with a naked singularity? I find that's a very good question. It's one of the family of questions that one would like to address in this topic. Another question, of course, that people ask about this is how about the rest, right? R cubed and so forth. And I tried to stave off that question by at least arguing that there might be an interval, a range of scales at which this theory is the relevant one. But ultimately, when you get to very high energy or very small distances, the rest of the theory is going to clearly come in. But perhaps these solutions are indicative of some of the behaviors that you have in these effective theories when you do include the whole picture.
Any more questions? Okay, let's thank Kellogg again.